is a set of basis vectors for the row space of T2 tilde. So T2 will only have linearly independent rows in that, which spans the row space of T2 tilde, which is the right-hand side of condition 1. And T3 is L tilde AT2, where we only pick the rows of LA that doesn't belong to T2. So these additional rows in here, which is T3, right, which is the left-hand side of condition 1, is the rows of LA that doesn't belong to T2. So obviously, if condition 1 is satisfied, this doesn't exist, because all of LA belongs to T2, means condition 1 is satisfied. There are no linearly independent rows in LA that doesn't belong to T2. So condition 1, I can write it like this. It's that, we've seen that. Now with the definitions of T2 and T3, we can say, okay, if rank of T3 is equal to rank of T2, well, it's the same as that. And of course, it's the same as saying the row space of T2 must equal the row space of T3 if we want to satisfy condition 1. So that's condition 1. So what I try to do here is to show, geometrically, how to find the minimum dimension matrix L that satisfies condition 1 and 2. So firstly, we will try to satisfy condition 1. So this is the whole of Rn space. So inside that, I can imagine all the vectors. But in order for me to do that, I only need to consider a finite number of vectors, n basis vectors for Rn. So I can think of n vectors inside this big circle. Now inside circle phi, before I talk about that, we have this definition T30. Remember the definition of T3, and T30 is when I choose L equal to L naught. So it's the corresponding matrix T3 when L is equal to L naught is T3 naught, right? So inside this circle phi, I can find all the basis vectors for T3, T3 naught. So I've chosen L equal to L naught. Inside circle 4, well, again we have T2 naught, so chosen L to equal L naught. Inside circle 4, I can find all the basis vectors that spans the row space of T2. Obviously, if L equal to L naught satisfies condition 1 to begin with, circle 4 and 5 will overlap. They'll be on top of each other. But this is the general case where they don't overlap. So the condition 1 is not satisfied, and we want to try and satisfy condition 1, or find the minimum dimension matrix L that satisfies condition 1. All right. Before we look at how to find the minimum dimension matrix L that satisfies condition 1, let's look at a few other circles. This circle here, inside circle 2, is the row space of C and L naught. So the vectors, row vectors in C and L naught are inside here. The row vectors of L naught are inside here, right? So these are basically vector subspaces. Now this circle 6 states that row space of T2 beta is equal to row space of T3 beta. So essentially I've chosen L to be L beta now, because remember we looked at T2 0 and L was L0. So now we're looking at T2 beta. So that means I have a matrix L beta such that the row space of T2 beta is equal to row space of T3 beta. So with L beta, we have satisfied condition 1. Now how we satisfy that, we'll look at it. Now what is L beta? L beta has all the rows of L naught, which is all the vectors in this space, right? And remember that was C vectors, row vectors of C is inside this space here, and vectors inside this space between 2 and 4 circles is the rows of CA. Rows of CA. Because remember inside 4 was T2, and T2 is CA, C, and L. Right? So between 2 and 4 is CA. So what is L beta? L beta is everything we can find here and everything vectors we can find here. Basis vectors you can find between 4 and 6. But I haven't still told you how to find it. Okay, I think we'll look at how to find it. Okay, so we start with T2 here, and T3 is circle 5. Now if we want to add rows in order to L naught, in order to satisfy condition 1, these vectors here has to be included. The vectors that you find between 4 and 5 has to be included, so that there is also a chance that T3 will not increase, because these vectors here already belong to T3.